Everybody, happy Tuesday. So, couple of announcements. This week we're gonna have a quiz, fourth quiz of the semester, okay? And then 1 week from this Friday we're gonna have our second in-person exam. So same drill. All right. Do we have any questions, concerns, comments before we begin? Oh, one other thing I want to mention right away. So I know that some of you missed homework assignments, like like for exam 2B. If you're one of those students, don't worry about it. I'm going to, if you remind me, like next week in class, okay, I will reopen, the homework assignments related to exam 2B, so that you can complete them before before you take the exam 2B. Okay. So, but I mean, don't miss that. So that's going to be your last opportunity. I mean, it's going to be a 24-hour window or something like that. Make sure that you complete them within that window. And also, if you haven't started working on your worksheets yet, all right, they have been open for at least 2 weeks now. It's high time that you start working on them. Okay. So remember those worksheet discussion worksheets, past exam questions is going to only help you, understand the material and do better on exams. So if you have some time, right, just do maybe at least 2, 3 problems, when you get a chance. Okay, at a time. All right. Any questions, concerns, comments before we begin? Anything? Okay. So if that is the case, I'll give you 1 more minute for discussion on the screen and then we will discuss it. Go ahead. 1 minute in your groups. Right, we have 85% chances now. All right, we have more than 90% answers. Therefore, I'm going to close this question in 5, 4, 3, 2, and 1. Okay. So here are our responses. Okay, most of us are between A and C. Most of us said it's A. Okay, which is the correct answer as well. Now, what I don't know why anybody would pick B or D because it's in the middle, right? It's going to be either like this or this. I can understand that, but what is involved here is this. We know energy of a photon is given by this relationship hc over lambda. Okay, so in other words, energy is inversely proportional to the wavelength. Okay, and we know 1 over wavelength is what do we call 1 over wavelength? Yeah, thank you, that's called the wave number. Therefore, energy is directly proportional to the wave number. Okay, so what is given to you here is the wave number or 1 over wavelength. Okay, so we have the smallest wave number for CO stretching. Therefore, they should have the lowest energy. Okay, OH on the other hand, I mean, takes more energy because how do you know that? Because it is occurring at a higher wave number. That is it. All right. What questions, concerns, comments do we have at this moment? Anything? Any questions, concerns, comments? Okay. So if that is the case, let's calculate that energy. Oh, by the way, this is the 7th time we are using this equation to calculate, since we introduced this equation, okay, energy. So can we calculate the energy for CO stretching? Here we go. Let's keep that aside. Now, what we want to do is to focus on this peak over here, zero stretching. It's around 1000, so I'm going to use 1000. And then I will go to my notebook and clear my doodling, and let's try this here. Okay, one more time. The only equation we're going to be using to calculate the energy is, okay, energy is equal to hc over lambda. And then out of these, we know h, we know c, because these are constants. And then even though we are not given the wavelength directly, we were given the wave number, which is 1 over lambda. 1 over wavelength, which happens to be 1000 per centimeters. Okay? So if that is the case, the wavelength must be inverse of this. Therefore, it should be 1 over 1000 centimeters must be the wavelength. But we want this in meters because my speed of light is in meters per second. So I want my wavelength to be in meters too. Therefore, I'm going to multiply this by 10 to the power of negative 2. Why? That's how many meters we have in a centimeter. Okay. So centimeters cancel out. You're going to get the answer in meters. That's going to be 10 to the power of negative 5 meters. That's it. We're done. Okay, this is the only thing that you need to do there. Okay, and now plugging and chugging. So if you plug in the numbers, H is 6.626 times 10 to the power of negative 34 joules seconds. Notice that I always write units. I mean, most of the time. All right. And then the speed of light is 3 times 10 to the power of 8 meters per second. And then I have the wavelength to be 10 to the power of negative 5 meters. Meters cancel out, seconds cancel out. You're going to get the answer in joules. If I do the numbers here, it should be 10 to the power of negative 29. And then 3 times 6 is 18. This should be 618 again. It should be 19.8 times 10 to the power of negative 21 joules should be an answer. So if we can rewrite this, it should be 1.98 times 10 to the power of negative 20 joules. Okay, this is one of your answers. This is joules per photon, and if you want to convert this to kilojoules per mole, I need to multiply this by the Avogadro's number, which is 6.022 times 10 to the power of 23, because this is how many photons we have in a mole of photon. And maybe divide this by 1000, because that's how many joules you have in a kilojoule. The joules cancel out. You're going to get the answer in kilojoules per mole. So this is 20. This cancels out. You have essentially 2 here. 2 times 6 is 12. So it's like 12 kilojoules per mole. I mean, if you don't have a calculator, that's what I would do. Okay. All right. What questions, concerns, comments do we still 100 1 meters 100 centimeters? That's the conversion.
Okay.
Yeah. That's always the case. It's just like 1 nanometer is 10 to the power of negative 9 meters. Okay, 1 centimeter is 10 to the power of negative 2 meters. Yeah, it's a conversion. I got that from, let's say, Google or ChatGPT or something like that. All right. What other questions, concerns, comments do we have? All right. So again, this is the 7th time we did a calculation like this like this since we introduced this equation. So this is it. I think that this is one of the toughest calculations you can get from this relationship. I mean, as you can see, it's not that bad. It's the same thing over and over. All right. So with that, let's do this. All right. Before I open the next question, can somebody tell me the last thing we wrote in our notes on last Thursday? What did we write? Yes, Grace. We wrote. Can I have the microphone here, please? He is. Okay, perfect. There you go. Thank you. Chris, what did you write?
Infrared spectrum tells us what types of bonds are in a molecule.
Thank you. Can you repeat one more time so that everybody can listen to that?
Infrared spectrum tells us what types of bonds are in a molecule.
Thank you. That is it, right? It's a period, right? So one more time. Towards the end of last Thursday's lecture, we wrote in our notes that infrared spectrum tells us what types of bonds we have in a molecule, period. That's it. Okay. So keeping that in mind, or some other things, let's try this. All right, I think there should be enough time for discussion. I'm going to close it in 5, 4, 3, 2, and 1. One more time, okay? The infrared spectrum tells us what types of bonds we have in a molecule, and that's it. It doesn't tell us how many, okay? It just tells us what types of bonds we have, okay? So this infrared spectrum tells us in our molecule, we have at least one OH bond, one CH bond, and one CO bond. That's all we know, okay? So correct answer is not 2. We need more information to do that. All right, I'll reopen that. This is just all right. All right. All right. What questions, concerns, comments do we have? I just wanted you to pay attention to what we just wrote there. This is the only reason that we have a question like this. Okay. To acknowledge that infrared spectrum only tells us what types of bonds we have, and that's it. Cole, go ahead.
So why do we need more information?
So how many CH bonds do we have there?
Well, it says 2 CH bonds.
No, I mean, no, it says that we have CH stretching occurring around, I don't know, 2,800, and the CH bending occurring around 1,400. That's all it tells us.
So it doesn't actually tell us how many?
No, that's exactly what I said. Yeah. Yeah, it doesn't tell us how many. It just tells us what types of bonds we have.
Oh, okay.
Yeah. So to know how many bonds we have, we need to know something like molecular formula or something like that, which we're going to get from mass spectrometry. Yeah. All right. Any other questions, concerns, comments? Okay. So with that, let's try. All right. Some of us do not want to change our answer. Okay. All right. Sticking to our guns. I appreciate that. All right. Let's try this. I feel like I'm missing a question here, but that's okay. So I'm going to close this question in 5, 4, 3, 2, and 1. All right. So before I get to your answers, I just want you to appreciate one thing, okay? So you can see that in this question, they are trying to combine 3 techniques: combustion analysis, mass spectrometry, and IR spectroscopy. Okay, this is what we usually do when we have an unknown compound. We conduct these 3 analyses to determine the structure of the molecule. Okay, so because if you have just combustion analysis and mass spectrometry, we can get the molecular formula. All right, but to get the types of bonds you have or the structure of the entire molecule, we need more information like IR spectroscopy. Okay, I just want you to appreciate that. However, so based on the answers given to you, the usefulness of combustion analysis and mass spectrometry is kind of questionable. The reason is all four of our options have the same number and types of atoms, meaning all of them have the same molar mass. Okay, because molar mass is the most important information we get from mass spectrometry. Because all of the options have the same molar mass, the mass spectrometry is kind of moot. Okay, so we have to resort to IR spectroscopy at this moment. All right. So based on the IR spectrum provided, we can eliminate option 1 immediately. Why? We do not have C double bond O in the IR spectrum. If it is not in the IR spectrum, it has no business being in the molecule. Same thing with option 2. We have a C double bond O. Okay, we do not have a C double bond O according to the IR spectrum. Therefore, 2 is out. Okay, option 3 is out. Okay, so option 3 is out. Okay, now keep in mind. So this kind of bond, right? Hydrogen having more than one bond might be possible maybe at ASU, but not here. Right? So hydrogen almost always form only one bond unless you are from ASU or you are taking an advanced level inorganic chemistry class where we have bridging hydrogen, You know what I'm talking about, right, Joy? All right. Anyway, so this is out. And also in our IR spectrum, we don't have such bonds, so that is out. And that leaves option 4 to be our correct answer. That's it. All right. Now, just for completion of our analysis, in the IR, we have CH bonds. In the molecule, we have CH bonds. In the IR, we have OH bonds. In the molecule, we have OH bonds. In the IR, we have CO single bonds. And in our molecule, we have CO single bonds. So all of them tally. All right. Therefore, the correct answer is option 4. All right. I'll give you 30 seconds to think about this, talk with each other, and make sure that we are on the same page. And I'll take your questions after that. Go ahead.
Okay. Yeah.
Just assuming that Rockstein has an own.
Yeah. So we are kind of looking at this information.
Yeah. They're not.
Kind of looking at this right now. Well,
You have to know that. You either know that or you don't. That's not a matter of what type of bond they're going. So that's none of the information except for is relevant.
All right. All right. What questions, concerns, comments do we have at this moment? Yes, Cole, go ahead.
So then,
please pay attention.
how are the types of bonds for how are the CH stretch and CH bend bonds represented in number 4? Because it's just a single line. How are we supposed to know whether that's the stretch and the bend? It doesn't mean anything. It's not correlated at all. It just shows what types of bonds there are.
Exactly.
So
yeah.
you just have to. So is that a case where you just have to know what types of bonds it can or cannot exist?
No. So you are given the IR spectrum. It tells us we have CH bonds. That's it. All right. So whether it's CH stretching or CH bending doesn't matter. CH stretching is elongation of the bond, and CH bending is when you have two bonds. I mean, it can have scissoring or wagging motion, but it doesn't matter. All that matters to us is, according to IR spectrum, we have CH bonds in our molecule. So that's it.
But every other one has the CH bonds as well.
Come then again.
Every other one has the CH bonds. As
Yeah,
well.
all the other molecules have CH bonds as well, but on top of that, they have some bonds that are not in the IR spectrum. That's why they are invalid.
Okay.
It's like solving a puzzle. Mhm. All right. What other questions, concerns, comments do we have? All right. So, Maya, are we getting a question about bending and stretching? All right. So, okay, for once and for all, please pay attention to this, okay? When you say stretching, it's pretty straightforward. The bond distance or bond length changes. That is stretching, okay? When you say bending, it's not talking about bending of a bond, all right? The bonds do not bend like that. So when they say bending, they're talking about motion of like two CH bonds, like they can go like this or like this, okay? Those are called bending motion, All right. So they have a different vibration frequency than stretching, and that's why you have them, separately in the IR spectrum. Okay. All right, but it doesn't matter to us if you see CH. If you see CH bonds in the IR spectrum, we have CH bonds in our molecule. That's all that matters to us. All right. Any other questions, concerns, comments? You have a question, Alexandra? Go ahead. Stretching is like stretching a rubber band. The bond can be stretched like a rubber band, and then bending. You know what? I cannot animate myself, so maybe I can do this. Maybe. There you go. So I clear my doodling. So these are bending motions. Alexandra? Okay. All right. Anyway, I'm not going to test you on, anything like this, but, this is just for, understanding what stretching and bending means. Okay. All right. So with that, what I want to do is, where were we? All right. So we know IR spectra tells us what types of bonds we have. After analyzing thousands of IR spectra, scientists have seen that these molecules on this slide represent the number of bonds an atom, like certain element can make. For example, if you take carbon, how many bonds does carbon form here? Everybody, how many bonds? Four bonds, right? How many bonds do we have for this carbon? Yeah, 4 again. How many bonds for this carbon? 4. How many bonds for this carbon? Right. Here's the question for you. How many bonds does carbon usually form? 4. There you go. So therefore, the common bonding pattern of carbon or common bonding capacity of carbon is 4. All right. So what I want you to do is I want you to look at the other molecules as well and determine how many bonds they usually form. Here we go. Four, 3, 2, and 1. All right. And here are responses. Look at that. It's beautiful. So these are the correct answers as well. 94% we can see, yeah. All right. So carbon 4 bonds, hydrogen 1, sulfur 2, nitrogen 3, oxygen 2, phosphorus 3, fluorine and chlorine only 1 bond, and then what else? Yeah, I think that covers everything, right? So that's what we notice here as well. Now here's the thing: you need to know the common bonding capacities of elements that form covalent compounds. You need to know this, right? I'm not asking you to memorize this, all right? But you need to know it. Okay, there's a difference between, knowing and memorizing them, You know that, right? Okay, so I know Donald Trump, right? He doesn't know me, but, but I never memorize his name. I mean, I just know him. Just like that, when you see him, you need to know. All right. So same thing goes here. So when you see an element, you need to know what the bonding capacity is. Okay. So to do that, please do not try to memorize it. I want you to pay attention to, let me go here for a second, to this table called periodic table, a beautiful table. Okay. So when you have this in front of you, okay, you should be able to determine the bonding capacity of any element in a covalent compound. All right. For example, let's start with this. Helium, neon, argon, all right, or krypton, this column over here, all right? How many bonds do they usually form? I heard that. How many? 0, right? These are noble gases. They tend not to react with anything. They form 0 bonds. Move on over. Fluorine, chlorine, bromine. How many bonds? Everybody, thank you. 1 bond. Move on over. Oxygen, sulfur, selenium. How many bonds? 2. Move on over. Nitrogen, phosphorus. How many bonds? Move on over. Carbon, silicon. How many bonds? There you go. That's it. Right? That's how you know how many bonds an element make in a covalent compound. All right. What questions, concerns, comments do we have at this moment? Anything? Any questions, concerns? Yes, you have a question, sir? Can I have the microphone here, please?
Oh,
I think Dylan
oh,
got it. Thank you, Joy. Yeah, go ahead. What's the
Sorry,
name, sir, one more time?
Lux.
Lux, go ahead.
Sorry, so but how many bonds would hydrogen have?
Hydrogen one. Okay, always just
So
one.
it would go from one, and then beryllium would be two.
Do it again?
The next column over would have two bonds, or
No, no. So you're talking about
magnesium, calcium.
no. They don't form covalent bonds.
Okay.
Yeah. All right. So Lux's question is okay. So here's the thing. When it comes to covalent compounds are made by, listen to this, very important, non-metallic elements, right? Non-metallic elements in the periodic table are restricted to top right corner of the table. Okay, only these guys are, participating in molecular formation or covalent bond formation. Therefore, we will only focus on these guys. Okay, the other guys, like majority of these elements are metallic elements. They form different kinds of bonds, like metallic bonds and ionic bonds, which we will talk about a little bit later. But these common bonding capacity, we do not even talk about common bonding capacities of these elements. All right, Lux, does that answer your question? Yeah, okay. All right. Now, keeping that in mind, now we know the common bonding capacities of elements. What I want to do during the rest of the time is to try to explain this. Okay? To explain the common bonding capacity of the elements, we need to look deeper into the atom. To do that, we are using, actually, you know what, two techniques, but before that, let me try this. Let's do discussion and then come back to that explanation, okay? Dylan, you have a question? I'll come to you.
Okay.
All right, I think we have close to 90% answers now. I'm going to close this question in 5, 4, 3, 2, and 1. All right. So nitrogen, common bonding capacity is 3. Chlorine, common bonding capacity is 1. Right? So with 1 nitrogen, you can combine 3 chlorines like this to form this compound. Right? We can write the chemical formula as NCl sub 3. Yeah? All right. What questions, concerns, comments do we have? Anything? Any questions, concerns, comments? Okay. All right. So if that is the case, here's what we want to do. Let's try to explain this common bonding patterns of elements. Okay. All right. To do that, we'll be looking into the atoms, and more specifically, we'll be using 2 techniques: X-ray crystallography and first ionization energy, at least today. Okay. So with X-ray crystallography, we're going to get information about the atomic size or atomic radius. And then the first ionization energy tells us information about how easy it is to, or how easy or how hard it is to remove 1 electron. Okay. So let's start with the atomic size, courtesy of X-ray crystallography. Okay. I do not expect you to know how X-ray crystallography works. Okay. Only thing I want you to know is that we get the atomic radii or atomic radius information or atomic size information from X-ray crystallography. Now, just to remind us about what the atom size is, okay, if you can remember, if we compare the atom to a football stadium, okay, the size of the nucleus is like the football at the center of the football stadium. Okay, the rest of the space is determined by what? Thank you, the electron cloud. So electron cloud determines the size of the atom. Okay, now what we want to do is we want to think about how this electron cloud size changes across a period in a periodic table and down a group. Now, what do I mean by across a period and down a group? Now, remember this, when it comes to periodic table, we have rows, right? So here's the first row with only 2 elements. That's our first period, okay? And the second period goes from lithium to neon. Third period goes from sodium to argon and so forth. Okay, these are called periods. All right, make sure that we know this, periods. Okay, and then on the other hand, the columns in the periodic table, like for example, the first column over here is called the first group, group 1. Okay, and then so you can take any column these are called groups, halogen group, okay, and so forth. So those are called groups. So groups are columns. I cannot draw, but I'll try. Okay. So this just to make sure that we understand what is meant by a period and what is meant by a group in the periodic table. Okay. What questions, concerns, comments do we have? Anything? All right. We understand what a group is, what a period is. And now, with that, I'm going to show you some data. Just tell me what you see. Here we go. Here are size data. Okay, if you can see, you have atomic radius on the y-axis and the atomic number on the x-axis. Okay, and you get 2 questions. What do you say? How does the atomic radius changes across the period, and how does it changes down a group? Go ahead. If you have already submitted your answers, if you can try to explain this, okay, that would be really productive. Okay, how can we explain these trends? I'll give you a hint. So just like any other things scientists explain, whenever the scientists are asked to explain something, they use a model, right? They are also using a model here. This model is called the shell model of the atom. Okay. Can we use the shell model of the atom to explain these trends? That's the follow-up question. All right, I think we have more than 90% answers, so the question is closed already. Okay, so what did we see? I will summarize and then we'll look at your answers, okay, one more time. So first period goes from hydrogen to helium. The size has decreased. A second period, lithium to neon, you see that in general, the size is decreasing. Same thing with the other periods as well. When you go across the period from left to right, okay, the size of the atom decreases. That's the first thing, first observation. And the other one is down a group. For example, lithium, sodium, potassium are in the same group. Okay, so when you go from lithium to sodium to potassium, the size of the atom increases. Okay, here's the same thing over here. Lithium, sodium, potassium are in the same group. When you go down the group, the size of the atom increases. Same thing with the other groups as well. When you go down the group, the size of the atom increases, okay, as well. Those are our observations. How do we explain this? Any ideas? Yes, sir. Thank you. Can I remind me your name some more time?
Brendan,
Brandon, go ahead.
when you're going down a group, you're gaining another valence shell, right? So that
Thank you.
is larger.
Yeah, let me repeat what Brandon said, okay? So when you go down a group, you are adding a shell. Each added shell is larger than the previous one, and that's why the size of the atom increases. Okay. Now, anybody who wants to have a stab at like periodic trend, like across the period, size decrease. Why? How can we explain it? Brandon, okay? Yeah. No, let's talk to you. What's your name, sir? Arjun, how can we explain why the size decrease across the period? Give me a second, Arjun. Let me show you a picture as well to aid your explanation. Here we go.
While you move across a period, you're gaining electrons, so the charges is like they're more attracted to each other, so that's why they're like decreasing in size because they're attracted to each other more.
All right. So, I mean, yeah, but you're getting the electron, but that is not the main reason why the size decreases, Arjun. But I mean, I think what else are we gaining across the period, Brandon?
The positive charge is pulling in the electrons tighter.
Thank
So it's
you.
getting smaller.
Exactly. Okay. Okay. So let's think about this. All right. Lithium to neon is the second period. All right. So each period is a shell, right? So now when you go across the period, you are adding protons to the nucleus. As a result of that, the nuclear positive charge increases. Therefore, the electron cloud is going to get more and more attracted towards the nucleus, making the electron cloud smaller and smaller and smaller as you go across the period. Okay, and that's why from lithium to neon, the size of the electron cloud or size of the atom decreases, because when you have more and more protons in the nucleus, these electrons are getting more and more attracted. As a result of that, the size of the electron cloud decreases. Okay. All right. On the other hand, you can see that when you go from neon to sodium, yes, we have added one more proton, but the caveat is the added electron, the 11th electron is not added to the same shell. It is added to a new shell, which is larger than the previous shell. And that's why when you go from neon to sodium, there's a huge jump in the size of the atom. Okay. You can see here's neon, here's sodium. Here, why is this huge? I mean, why is there a huge jump here? Because this 11th electron is added to a new shell, which is much, much larger than the previous shell. Okay. Then again, in the third period, you are adding the electrons to the same shell. So it decreases, down to argon. And then after argon, the next electron is added to a new shell. And that's why there's a huge jump. Okay. And these are called periodic trends. And shell model nicely explains that. All right. What questions, concerns, comments do we have? Okay. So I'll take you, I'll walk around. If you have questions, you can talk to me privately as well. Meanwhile, what I want to do is I want you to summarize what we noticed for the second period at least. Okay. That's the most popular answer. And that's the correct answer as well. So in other words, across the period, okay, we see that in general, the size of the atom decreases. Okay. For the first approximation, okay, it decreases. Okay. It's not necessarily linear, but it decreases. That's the idea here. All right. Now, let's think about energy for a second. Okay. So how does the potential energy changes across the period? Okay. And remember, why did the size decrease? Size decreased because you have more protons in the nucleus. Therefore, this electron cloud was more attracted towards the nucleus. Okay. In other words, stronger attractive interactions between the electrons and the nucleus. That's why the size of the atom decreased across the period. Now, keeping that in mind, can you tell me how you would expect the potential energy to change change across the period? Go ahead. This is question in 5, 4, 3, 2, and 1. And here are our responses. Yeah, I like it. Okay. So lithium has the highest potential energy. Why? Weakest attractive interactions between the nucleus and the electron cloud. And neon has the lowest potential energy. Why? The strongest attractive interactions between the nucleus and the electron cloud, because it has the most number of protons. Okay. So for a first approximation, we can say that if this was my 0, okay, the potential energy decreases across the period for a first approximation. It's not exactly linear, but just for our understanding. All right. Now, there's something else I want to mention here, and that is the energy required to remove one electron. One electron. Okay. This is known as first ionization energy. Okay, because you're by removing an electron, you make the atom an ion. Okay, because you're only removing one electron. This is called the first ionization energy. In short, the acronym is FIE. Okay, so what I want you to do is think about how the first ionization energy changes across a period. Okay, so we already know neon has the strongest attraction towards the electrons, making it the smallest atom. So the question is, will it has higher ionization energy or lower ionization energy compared to something like lithium? All right, I'm going to let you decide that in this question. Here we go. Well, almost 80% of us got that. Okay. One more time. For a first approximation, the lithium will have the lowest ionization energy in this period, and then neon will have the highest. Why? Neon has the highest number of protons in the nucleus. Therefore, it's going to hold on to the electrons more strongly, and that's why it is harder to remove electrons from neon compared to lithium. All right. All right. So I'm going to stop right here. When we come back on Thursday, we will talk about photoelectron spectra. Bye, everybody. Have